Hello and welcome to lesson 1-7. 1-7 is titled Debt, Bad, Chocolate Good. You are going to be learning about scientific notation in this section. The first part of this page, on page 89, tells us a little bit about why we might need scientific notation. Scientific notation is very helpful for writing very, very large numbers or very, very small numbers. It's a shortcut way of writing them so we don't have to write all the zeros out. Towards the bottom of this page, section 1-7, the classwork starts, and it talks about the national debt. It says if you tracked the national debt over the last 90 years, you'll notice that it's exponential growth. That's that type of growth that we learned about in section 1-4. It's curved. On average, the debt has grown by about 7.9% each year. If this trend continues, by 2050, the debt will be a very, very large number, and by 2100, it'll be an even bigger number. And if you're like me and most people, these numbers are just too big to even have any understanding about what they mean. So what we'd like to do is maybe write them in a different form so we can more easily compare them. We're going to start with an easier example. They start with 300, and they mention, hey, you know what? You could write 300 as 3 times 100, which is then 3 times 10 to the second power. That may seem silly because 300 is not that hard to write, but it's getting us ready to write bigger numbers. So the next thing we do is compare the powers of 10. 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1000, 10 to the fourth power is 10,000, and 10 to the fifth power is 100,000. Do you see a pattern? 10 to the first power had 1 0. 10 to the second power had 2 zeros. 10 to the third power had 3 zeros. 10 to the fourth power had 4 zeros, and 10 to the fifth had 5 zeros. So putting another power on 10 adds another 0 to the number. So it's certainly going to give us a nice way to write shorthand numbers. So they give me a number. They talk about 5 billion. 5 billion is a really, really big number. You see that it has 9 zeros. As a shortcut, we could have written that as 5 times 10 to the 9th power to represent those 9 zeros. Towards the bottom of this page, they go back and revisit national debt. In 1930, the national debt was about 16 billion. By 1985, it had grown to 1.823 trillion. Again, hard to compare unless we write it into the scientific notation. In 1930, that 16 billion can be written as 1.6 times 10 to the 10th power. For 1985, I can write the 1.823 trillion as 1.823 times 10 to the 12th power. So now I can see that the exponents are different. From 10 to 12, that's a significant change. An extra 2 zeros. At the top of page 90, they're getting us ready to write numbers into scientific notation. They remind us that if a number is in proper scientific notation, the first part of the number has to be between 0 and 10. So it gives us a nice way to compare. We can compare those numbers, and then we can compare the powers. In number 1, they tell me that Earth is about 2.57 times 10 to the 7th miles from Venus, and 4.67 times 10 to the 9th miles from Pluto. We want to calculate how many times further away Pluto is. And the little hint says, be careful, it's more than just the exponent. So let's start with the exponent. We went from 7 to 9, which means it's 10 to the second bigger, or 100 times further. But then we've got the 2.57 and the 4.67 that we should also compare. 4.67 is almost twice 2.57. So I'm going to multiply that 100 times 2, and I'm going to get 200. So we are going to say that Pluto is about 200 times further away. Towards the middle of this page, there's a purple box. Purple boxes are always important. There's something important to be learned in the purple boxes. And this one tells us how to take a number and write it into scientific notation. Large numbers, turning them into scientific notation. Step 1 is to write a decimal point at the end of the number and then move it to the left so there's just one digit before it. That one digit makes our number between 1 and 10. And then write times 10 to some power. That power will be however far you had to move your decimal back. They give us a nice example here. We had a very large number. You see that they put the decimal at the end. If you don't see a decimal, it's assumed to be at the end of the number. And they wanted it to be between the 3 and the 9. So they had to move back 1, 2, 3, 4, 5, 6 places. So you'll see that when they rewrote it into scientific notation, it's 3.968 times 10 to the 6th. And now they're going to let us do it. So we're going to try a couple on our own. So number 2 says, let's get this up higher so we can get them all in and not have to scroll too much. Number 2 says the number of people in the US in September 2021 was 333,228,000. So where do I want my decimal point to be? I want it to be between the first 3 and the second 3. So I'm trying to go right there. So it's going to be 3.33228. I don't need to write any of the zeros. Times 10 to some power. And that power is going to be however far I had to move my decimal. Well, my decimal wasn't shown, so I assume it's at the end. And I'm going to count how many spaces I had to move. I had to move 1, 2, 3, 4, 5, 6, 7, 8. So it's 3.33228 times 10 to the 8th power people. The moon, where do I want my decimal to be? I want it to be between the 2 and the 3. You always want one number to the left of the decimal point, so that becomes 2.389 times 10 to some power. And I'm looking to see where that decimal point is right now. It's at the end. I'm going to have to move it 1, 2, 3, 4, 5, so it's a 5th power. A general rule of thumb is that if you have a very large number, the exponent is going to be positive. If you have a very small number, the exponent will be negative. And that's where they're getting to at the bottom of page 90. We're doing some more powers of 10, but this time we are doing negative powers. 10 to the negative first is 1 over 10. 10 to the negative second is 1 over 10 squared, or 0.01. 10 to the negative third is 1 over 10 to the third, or 0.001. 10 to the negative fourth is 1 over 10 to the fourth, or 0.0001. So this time what happens, the pattern, is the more negative I get, the decimal moves one more point to the left. So the example given here is 0.03 is the same as 3 times 10 to the negative second. So at the top of page 91, we have another purple box, and they are showing us how to write small numbers into scientific notation. Same idea. You want to move your decimal so there's one number that's not a 0 to the left of that decimal point. And then times 10 to some power. That power will be negative because it's a tiny number. And it was how many places you had to move your decimal. So they gave you a nice worked out example here. It was 0.000437. We decided we wanted to move the decimal between the 4 and the 3. So it's 4.37 times 10 to a power, and we count how far we moved it, and we moved it 4 spaces, but notice it's negative 4. Again, tiny numbers have negative exponents, big numbers have positive exponents. So they're going to get us some practice doing this. We've got teeny, 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 tiny numbers, and they want us to write both of these into scientific notation. So the first one, I want to move my decimal all the way till it's after the 8. So it's going to be 8 times 10 to some power. It's going to be a negative power because it was a tiny, tiny number. We move 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 times 10 to the negative 8th power. For the next one, we'll do it in a different color just so it shows up here. We want to be between the 1 and the 2. So that one's going to be 1.2 times 10 to some negative power. And the power is going to be based on how far I had to move my decimal. The decimal is shown here. I had to move over 3, 6, 7. So it's going to be negative 7. Number 5, they talk about a bacteria. E. coli is a common bacterium that can cause intestinal issues. A typical specimen is a very, very tiny length, And I want to write that in scientific notation. My decimal needs to be after the 7, so it's going to be 7 times 10 to some negative power. That negative power is going to be however far I had to move it. So 1, 2, 3, 4, 5, 6, negative 6. All right, now they want us to do some comparison. Based on the size of the exponent in scientific notation, which is bigger, a flu virus or E. coli? So let's get a different color out here and circle these two. We had the flu was 8 times 10 to the negative 8th, and E. coli, which was 7 times 10 to the negative 6. The difference in the exponents is about 2. So 10 to the second is the difference, which equals 100. Let's make that 2 look a little better. Going to the next page. I can get up on the next page. Page 92. They're going to show us how to convert in the other direction now. So we are going to convert from scientific to decimal notation. So the idea still of if it's an exponent, a positive exponent, it's a really big number. Negative exponent is a really tiny number. So if the power of 10 is positive, you're going to move your decimal to the right, which makes it big. If your power is negative, you're going to move it to the left, which makes it a little tiny number. They give us a nice example here. So we took 4.01 times 10 to the 8th. They move it. They should have a really nice description there of how it's being moved, and then fill in the places with zeros. So 4.01 times 10 to the 8th became 401 million. 3.2 times 10 to the negative 5th goes the other direction. So it starts with a decimal and moves 5 to the left, and it's that very, very tiny number. So number 7 wants us to do the same thing. So we are going to take the 5.4 and move my decimal 6 places to the right because it's a positive exponent. I want my number to get bigger. So 1, 2, 3, 4, 5, 6. I'm going to fill each of those empty spaces in with zeros. And there's my number. We'll write it nicer. 5,400,000. Likewise, we're going to do the same thing with the 3.6 times 10 to the negative 9th. But this time we're going to be moving to the left because it's a negative exponent. We want to make our number much smaller. We're going to move 9 spaces. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of those spaces is going to get filled in with a 0. So I have 0 point, and how many zeros do we write in there? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and then the rest of the number. So you're probably starting to see why it is very advantageous to have scientific notation, because those zeros kind of get frustrating to write. At the top of page 93, they're going to ask us some questions to see if we really understand it. So when a number written in scientific notation has a positive exponent on the 10, what can we say for sure about the number? We could be a little more general and say it's a very big number. We could also say that it's got to be 10 or bigger, 10 or larger. The opposite of that is if we've got a number between 0 and 1, so it's a decimal when it's written scientific notation, what can we say about the exponent on 10? So it's one of these tiny numbers. It's not a big number with a bunch of zeros. It's a bunch of zeros, then a number with a decimal in it. We can say that the exponent is negative. Exponent is negative. Again, we're just wrapping up together what we've learned, making sure we understand all this. If number 10 says fill in the blanks. If a number in scientific notation has a negative exponent on the 10, to convert to decimal form, we will move to the left. Because the number is less than 1, or it's a tiny number. In my mind, big and small work better. The bottom of this page gives us some nice ways to put this into the calculator. So we can actually practice using the calculator. They give us a couple examples on the calculator. The first example talked about, if I can get the calculator turned on, what would we do if we did something like 990,000? I can't read it, I'm trying to read it in the textbook, but 990,000. So 99 and 4 zeros. 1, 2, 3, 4 times 125,000. So 125 with 3 zeros. If I put that into my calculator, I get this weird number back. But what they want you to recognize is that number is scientific notation. This is the way your calculator writes scientific notation. That is 1.2375 times 10 to the 11th. The little EE on there, or the little E, some calculators use EE, is times 10 too. And then they also show me an example that I can actually do stuff right in scientific notation. And they show me the buttons to hit. So I'm going to do 1.5. And to get that E button to pop up, I have to hit the second button and then the comma, and the little E appears. And then my power was 12. And I'm multiplying that by 3.2. And then again, I have to hit the second comma to get the E to show up. And that was a power of -8. And it gives me my answer as 48,000. And I could rewrite that into scientific if I wanted to. It would be 4.8 times 10 to the 4th power. And I know that's positive because it's a big number. You could also completely turn your calculator into scientific mode. It's a little bit weird to do that because everything you do, if you don't turn it back, will be in scientific notation. But they use the example of that 99 times 125, which my calculator was able to handle before. It gives me this number. If I actually want the calculator to force it into scientific notation, I go to the mode, which is right next to the second button, and I arrow over, so I'm moving it into scientific notation. And then I hit second mode to get out of there, and I do the hit enter, and there it is in scientific notation. 1.2375 times 10 to the 4th. The weird thing is, if you do something simple on here now, like 6 times 12, it's going to put it in scientific notation, which we don't like. So go back to your mode, hit enter while it's on normal, and then that'll take us back into our normal mode. So your calculator is a very valuable tool. You just got to be careful and know how to use it. All right, let's go to the last page here. This is page 94. So they want us to write what the answer actually is. So they're asking, hey, do you know how to read your calculator? Well, I know how to read my calculator. I just learned that means 7.44 instead of E. That means times 10 to the 3rd power. So that's my answer in scientific notation. I also know how to convert that. I would move my decimal 1, 2, 3 places over, and the number in standard notation is 7440, or 7,440. All right, the last one is talking about what the different things mean. So 10 to the 2nd is the hundreds place, 10 to the 3rd is thousand, 10 to the 6th is million, 10 to the 9th is billion, 10 to the 12th is trillion. So they want us to complete this table. It's actually the second to last problem. And they have a couple filled in for me. I need this table up here too. So 1.6 times 10 to the 10th was closest to billion. That was the 16 billion. So we're talking about how to say these. This one, the next one is 5.1 times 10 to the 10th. So 5.1 times 10 to the 10th would be 51 billion. Just following the same pattern that we had in the first one. I won't jump up to trillions until I get to 12 or more. 2.57 times 10 to the 11th is 257 billion. 2.86 times 10 to the 11th is 286 billion. $3.71 times 10 to the 11th is 371 billion. I think the worst part about these is just writing them all out. Then I have bifocals, so I'm looking through the bottoms of them. Now, when I get to the 12th there, I have 3.233 times 10 to the 12th. That is 3.233 trillion. The next one is 5.674 trillion. Now the next one, I am up to the 13th power, and we know the trillion is 12th. So I have to move my decimal one place over. It's going to be 13.562 trillion. And the last one is also 13, so it's going to be 27.747 trillion. Those are some really big numbers. They do show you a nice graph of it. We did talk early in the lesson that this is actually exponential growth. Exponential growth has that curve as opposed to being a straight line. And then at the top of page 95, they say the population of the US was roughly 1.23 times 10 to the 8th power in 1930 and 3.3 times 10 to the 8th power in 2020. So we're talking the population of the country. If the national debt were to be paid off by dividing the total evenly among the citizens, what would each person have owed in 1930? Well, we need our calculator for this. So we're going to pretend that we're dividing all this out. So the national debt in 1930, I have to go back to my previous page, was 16 billion. It was 1.6 times 10 to the 10th. So I'm going to type in 1.6 and then use my EE button to the 10th. That was 1930. And then divide that by the population in 1930. The population in 1930 was 1.23 times, whoops, not times. I just cleared it all. Let's start that again. The population, or the debt in 1930 was 16 billion. So we said it was 1.6, my EE button, to the 10th power. This is coming from the previous page. And I want to divide that by how many people there were. So there were 1.23, second, comma, to get the EE button on there again, to the 8th power. So each person in 1930 would have had to pay about $130. So we'll go ahead and write that one down, and then we'll do what we'd have to pay a few years ago. The second part asks me what would we have to pay in 2020. So I have to find from that page 94 the debt in 2020, which was 2.7747, second, comma, to the 13th power. That's when we're in the trillions. Divide that by the population in 2020, which was 3.3, second, comma, 8th power. And we would each need to pay, oops, I forgot to hit enter, $84,000. So $84,000, pull my calculator back up to get my change, and $84,082. So $84,082. So you can really see that the debt has grown much faster than the population has. And the next thing you'll be working on is your group. And I hope you have a wonderful day and a wonderful week.